Let us learn about limits. For example, if we write limit x tending to a of f of x, this is the function and this is the limit, and this should be read as x tending to a or x approaches a. So by finding limit x tending to a of f of x, we are finding for which value f of x approaches to as x approaches to a. Limits are very important fundamental concepts of calculus and are used in continuity and differentiation as well as integration. For example, if we have limit x tending to 2 of x plus 2, the function is x plus 2 say. So here we don't have any problem, we can directly substitute because the function is defined at x is equal to 2. So we can directly substitute the limit value. So as x approaches 2, the function x plus 2 approaches the value 4. This arrow mark means tending to or approaches to. Now see this example. Limit x tending to 2 of x square minus 4 divided by x minus 2. And the function is not defined when x is equal to 2. So we cannot substitute the value x is equal to 2 directly here. So sometimes we cannot directly substitute the limit value, but we can see what the function value approaches to when x gets closer and closer to 2. For example, let us take the values of x and the values of f of x. This is the function f of x. Let us take 1.9. If you calculate, the answer will be 3.9. And for 1.99, the answer will be 3.99. And for 1.999, we get 3.999. And as we approach, for example, let us take this value, and it will give you 3. This. Similarly, let us calculate for 2.01. The answer will be 4.01. 2.0001 will give you 4.0001. As we approach 2, from the right hand side of 2 we are approaching. So the value here is 1. So we are approaching this value 2 from the left hand side of 2 as well as from the right hand side of 2. In that case, the f of x approaches 4. So we can say that as x approaches 2, f of x approaches the value 4. Actually, the value of the function at x is equal to 2 is not defined. But instead of trying substituting x is equal to 2, we are approaching 2. That is, we are going closer and closer to 2. In that case, we are able to find out the answer as x approaches to f of x approaches the value 4. We are not saying that f of x is equal to 4. We are saying that f of x approaches the value 4. So we are just ignoring what happens at x is equal to 2. And just we are getting closer and closer to 2 so that f of x goes closer and closer to 4. If you see the graph of this function, f of x is equal to x square minus 4 divided by x minus 2. The function is not defined at 2. There is a hole in this graph where the function is not defined. So in that case, x can approach 2 from the left side of 2 as well as from the right side of 2. So in such cases, we need to calculate the left hand limit as well as the right hand limit. From the table, we saw that as x approaches 2 from the left side of 2, 2 minus, we denote this as 2 minus. It is not minus 2. It is 2 minus, indicates that x approaches the value 2 from the left side of 2. Therefore, limit of x tending to 2 minus of this function x square minus 4 divided by x minus 2 is tending to 4. Similarly, if you approach the value 2 from the right side of 2, the function approaches the value 4. In this case, the left-hand limit and the right-hand limit both are equal. Therefore, we say that the limit extending to 2 of this function exists. If they are not equal, the limit does not exist. If we write limit extending to 2, that means 2 minus 2 plus both are included. For example, consider the graph of signum function. There is a gap in the function. So if there is a gap in the function, as x approaches 0 from the right side of 0 or from the left side of 0, the values are not the same. So in this case, limit extending to 0 minus of the signum function, that is absolute value of x divided by x, is minus 1. It is tending to minus 1. Whereas the right hand limit, this is the left hand limit, the right hand limit, limit extending to 0 plus of absolute value of x divided by x, that is the signum function. Look at the graph here. Here, as x approaches 0 from the right side of 0, the value approaches 1. Y value is 1. Here LHL and RHL are not equal because there is a gap in the figure. So in such cases, we say that limit extending to 0 of the signum function does not exist. So the limit allows us to examine the tendency of a function around a given point. Even when the function is not defined, we can find the limit value of that function. Now, for example, a question is given, say, limit extending to a of f of x. We will directly substitute the limit value in the function. So you may get the answer f of a may be equal to b. So the limit exists and the limit value is b, we say. Now you are applying this value a in f of x. If your f of x is b by 0, say, so the limit does not exist in this case. Now you are substituting the limit value in the function, and if you get 0 by 0 form, it is not defined. We call that as indeterminate form. In such cases, we follow one of these following methods. If you have a rational function, we can use factorization method. For example, if the question is like limit extending to 1 of x square plus 2x minus 3 divided by x minus 1. Here, after factorization, we will be able to apply the limits, or we can rationalize. For example, limit extending to 0 of root of 1 plus x minus 1 divided by x. When do we use rationalization method? When we have radical sign. Sometimes we have to rationalize the numerator, sometimes we have to rationalize the denominator. In some questions we have to rationalize both. And we may use substitution method, or we may use identities also. If it is a trigonometric function, we may use identities and simplify. Or apply the formulae. Substitution, for example, the question is limit extending to pi by 2 of tan 2x divided by x minus pi by 2. So here we get 0 by 0 form. So we may use substitution method here. We can take x minus pi by 2 as some other variable y, and we can apply the formula after that. Or see this question, limit extending to 0 of sin 2x divided by sin x. Here we may use the identity. If you apply the limit value, you get 0 by 0 form. Whereas use the identity, 2 sin x cos x in the numerator, sin x gets cancelled. Then we can apply the limit. Or formula. So we have formulae. I will give you the list of formulae. So using the formulae, we can find the limit value of the function. Okay, after doing these methods, then directly substitute the value. Here directly we are substituting the value. So after using this, directly substitute the value. After directly substituting the value, if you get this B answer, the limit answer is B. Or if you get B by 0 form, the limit does not exist, we conclude. And if you get 0 by 0 form again, try these methods once again. Limit formulae. We are not going to learn the derivations of these formulae, but these formulae can be derived using factorization or by sandwich theorem. Limit extending to a of x raised to n minus a raised to n divided by x minus a is n into a power n minus 1. Then next formula, limit extending to 0 of sin x divided by x is 1. Third, limit extending to 0 of 1 minus cos x divided by x is equal to 0. Remember, this can be used only when it is in the numerator. When it is in the denominator, we cannot use because division by 0 is not defined. And this one formula is enough to solve all trigonometric functions. Even this formula has been derived using the second formula. Limit extending to 0 of tan x by x is 1. Again, this formula also can be derived from the second formula because tan x can be written as sin x by cos x. Limit extending to 0 of sin x by x becomes 1 and cos 0 is 1. Therefore, the answer is 1. And limit extending to 0 of e power x minus 1 divided by x is equal to 1. And limit extending to 0 of log of 1 plus x divided by x is also 1. Now we should know for which questions we have to do LHL and RHL. And for some questions we can do directly combining LHL and RHL. If I write extending to a, that means limit extending to a minus and a plus both are included in that. If f of x has two different definitions, say, for example, for x greater than or equal to a and for x less than a, then we need to do LHL and RHL. So for LHL we use x less than a definition, for RHL we use x greater than a definition. And we have to see whether those two limits are tending to the same value or not. If they don't tend to the same value, we conclude that the limit does not exist. Then for signum function, that is absolute value of x by x, this function has a gap at x is equal to 0. For other values, it doesn't have any problem. This is also a signum function. And this has a problem at x is equal to 1. So it depends how the function is defined. And then absolute value function.
At x is equal to 0.
For absolute value function, always LHL and RHL will be same. But the definitions are different. That's why we do LHL, RHL. So it takes the value x when x is greater than or equal to 0 and minus x when x is less than 0. That's why we do LHL and RHL, but both will be same for absolute value function. This is the third one. Fourth, greatest integer function. If you remember the graph of greatest integer function, it's like steps. You have gaps in the graph at each integral value. Therefore, for greatest integer function, at all integers, the limit does not exist. When we come across such functions, we will do LHL and RHL to check whether the limit exists or not. Algebra of limits. Limit extending to a of f of x plus g of x. You have sum of two functions, and to apply the limit, we can separately apply the limits for each function. So limit extending to a of f of x, limit extending to a of g of x. Similarly for subtraction. And then the second one, product rule, limit extending to a of f of x multiplied with g of x. Here also we can take it as limit extending to a of f of x into limit extending to a of g of x only when both the limits exist. If one of the limit does not exist, don't apply the limit for the other function also. So you can combine and simplify and then try to apply the limits. The third one, quotient rule, limit extending to a of f of x divided by g of x. So we can apply the limit for the numerator as well as for the denominator if both of them exist. And here the denominator should not become 0. The fourth point, limit extending to a of, if you have a constant lambda times f of x, the constants are not affected by the limits. So they can be removed outside the limit. Therefore it becomes lambda times limit extending to a of f of x. Constants are not affected by the limits, so it will be c. Limit extending to a of a constant c will be c itself. And then limit extending to a of f of x raised to r. So we can apply the limit for the base and whole power r. It becomes. Limits of a polynomial. What do you mean by a polynomial function? For example, x squared plus 2x minus 5 is a quadratic polynomial, and x by 2 minus 1 by 10 is a linear polynomial. That is, powers of x should be positive integers. So if the function is a polynomial, we don't have any problem in applying the limits because all polynomials are continuous functions. There are no breaks in the curve. There are no holes in the curve. So directly we will be able to apply the limit value for polynomials. So they don't give us any problem. Now limits of rational functions. What do you mean by a rational function? A polynomial divided by another polynomial. So when we apply the limits separately for the numerator as well as for the denominator if both of them exist, and g of a should not be equal to 0. When you apply the limit, if you get 0 by 0 form, then use factorization method. Cancel the common factors and then apply the limit. So if you get b by 0 form, then we conclude that the limit does not exist. And if you get the answer b, that is the limit value. Now we will do exercise 13.1. We have very simple questions because we are beginners. We are just learning limits, so very simple questions are given. First question, limit extending to 3 of x plus 3. First, directly substitute the limit value and check. We get 6. The polynomials are defined for all real values. The function is defined at 3, so directly we are able to substitute the value. The answer is 6. Second question, limit extending to pi of x minus 22 by 7. The answer is pi minus 22 by 7. Pi is an irrational number, non-terminating, non-repeating decimal. So approximately the first few digits are 3.141592653, etc. But the value of 22 by 7 is 3.142857, etc. So we use 22 by 7 for the calculations because the first two decimal digits are same to make our calculations easier. But 22 by 7 is not the correct value of pi. Therefore, the answer is pi minus 22 by 7. There is a difference in these two values. Question 3. Limit r tending to 1 of pi r square. This is again a quadratic polynomial. We don't have any problem with polynomials because polynomials are defined for all values, all real values. So it is pi into 1 square, which is pi. Question number 4. Limit extending to 4 of 4x plus 3 divided by x minus 2. Check the denominator first. 4 minus 2. It doesn't become 0. So direct application of the limit value. 4 4s are 16 plus 3 divided by 4 minus 2 is 2. The answer is 19 divided by 2. Question number 5. Limit x tending to minus 1 x power 10 plus x power 5 plus 1 divided by x minus 1. Check the denominator. Minus 1 minus 1. It doesn't become 0. So let us apply the limit value directly. Minus 1 whole power 10 plus minus 1 whole raised to 5 plus 1 divided by minus 1 minus 1. Minus 1 raised to 10 becomes plus 1. And the second term is minus 1. Third term is plus 1 divided by the denominator is minus 2. The answer is minus half. Question number 6. Limit extending to 0 of x plus 1 whole raised to 5 minus 1 divided by x. Here we have a problem. We cannot substitute the limit value directly because the denominator becomes 0. One method is using the expansion of x plus 1 whole power 5, which is a longer method. Let us write this function as x plus 1 whole raised to 5 minus 1 divided by, the denominator can be written as x plus 1 minus 1. 1 and 1 will get cancelled. The denominator becomes x. Now this is of the form limit extending to a of x power n minus a power n divided by x minus a is equal to n into a power n minus 1. The function is in the proper form, but look at the limit. We should have x plus 1 tending to 1 because x tends to a here. We have the limits x tending to 0. So as x tends to 0, x plus 1 tends to 1. Add 1 on both sides, we get x plus 1 tending to 1. The limit is also in the proper form. Now we can apply this formula. N here is 5, a here is 1, n minus 1 is 4. Therefore the answer is 5. Question 7. Limit extending to 2. 3x square minus x minus 10 divided by x square minus 4. Check the denominator. 2 square minus 4, the denominator becomes 0. Let us try to factorize. I am factorizing the numerator. Product is minus 30, sum is minus 1. So minus 6x plus 5x. Minus 6 into plus 5 is minus 30. And addition gives you minus 1x. From the first two terms, 3x is common. And from the next two terms, 5 is common. Therefore, the factors are x minus 2 and 3x plus 5. Therefore, we get limit extending to 2 of, the numerator is x minus 2 times 3x plus 5 divided by, let us factorize the denominator, x minus 2 into x plus 2. Cancel the common factor. Now the denominator doesn't become 0. The problematic factor was x minus 2. Because of that only the denominator was becoming 0. Now we got rid of it. Apply the limit value. Therefore, the answer is 11 divided by 4. Question number 8. Limit x tending to 3 of x raised to 4 minus 81 divided by 2x square minus 5x minus 3. Let us check the denominator. Substitute x as 3. 9 2s are 18 minus 15 minus 3. Yeah, it becomes 0. This is a rational function. We will factorize. Let us factorize the denominator. Product should be minus 6. Sum is minus 5. So we will take it as minus 6x plus x and minus 3. Here 2x is common. We get x minus 3. Here 1 is common. Therefore, the factors are x minus 3 and 2x plus 1. We can factorize the numerator too. X square minus 9 into x square plus 9 divided by, the denominator is x minus 3 times 2x plus 1. Let us factorize x square minus 9, which is x minus 3 into x plus 3. Complete factorization is done. Divided by x minus 3 times 2x plus 1. Cancel the common factor. Now the denominator doesn't become 0. We will apply the limit value. 3 plus 3, 6. 3 square, 9 plus 9, 18. Divided by 2 3s are 6. 6 plus 1, 7. Therefore, the answer is 108 divided by 7. Question 9. Limit extending to 0 of ax plus b divided by cx plus 1. The denominator doesn't become 0. Let us apply the limit value directly. So we get 0 plus b divided by 0 plus 1. Therefore, the answer is b. Question number 10. Limit z tending to 1 of z power 1 by 3 minus 1 divided by z power 1 by 6 minus 1. Here we may use factorization method or the formula method. Let me use formula method. I am going to divide both numerator and denominator by z minus 1. It becomes limit z tending to 1 of z raised to 1 by 3 minus 1 by z minus 1. Similarly, the denominator becomes z raised to 1 by 6 minus 1 by z minus 1. Now we can apply the formula for both numerator and denominator. The formula is limit extending to a of x raised to n minus a raised to n divided by x minus a is n into a power n minus 1. Apply this formula for the numerator. N is 1 by 3. A is 1. 1 raised to any number is 1. Similarly, apply the formula to the denominator. N here is 1 by 6 and 1 power any number is 1. Therefore, the answer is 6 divided by 3, which is 2. Question number 11. limit x tending to 1 of ax square plus bx plus c divided by cx square plus bx plus a. And the condition given is a plus b plus c is not equal to 0. If you substitute the limit value, the denominator doesn't become 0. So directly we will substitute a plus b plus c divided by c plus b plus a, which is 1. The denominator should not become 0, that's why this condition is given. Question 12. Limit x tending to minus 2. And the function is 1 by x plus 1 divided by 2 divided by x plus 2. We will simplify the numerator by taking LCM. The LCM is 2x. The numerator becomes 2 plus x divided by x plus 2. Here we can cancel x plus 2 and x plus 2. Now apply the limits. 1 divided by 2 into minus 2, which is minus 1 divided by 4. Question 13. Limit x tending to 0 of sin ax divided by bx. Limit x tending to 0 of sin ax. I am dividing by ax and multiply by ax, and we have bx. We can cancel these two, or you may multiply and divide only by a. And we will apply the formula. Limit x tending to 0 of sin x divided by x is 1. And as x tends to 0, ax also tends to 0. Multiply both sides by a, ax tends to 0. Therefore, the formula is applicable. By the formula, it becomes 1, and we have into a by b. Therefore, the answer is a divided by b. Question 14. Limit x tending to 0 of sin ax divided by sin bx. To use that formula, limit x tending to 0 of sin x by x, we need ax here. So let us multiply and divide by ax. Similarly, let us multiply and divide the denominator by bx. Cancel these two x. We can apply the limit for the numerator and for the denominator. The formula is limit x tending to 0 of sin x divided by x is 1. As x tends to 0, ax tends to 0, bx also tends to 0. Therefore, formula is applicable for both numerator as well as to the denominator. The numerator becomes 1 into a, the denominator becomes 1 into b. Therefore, the answer is a divided by b. Question number 15. Limit x tending to pi, sine of pi minus x divided by pi times pi minus x. Without using substitution also you can do this question. Let us substitute pi minus x as t. So x will be pi minus t. As x tends to pi, t tends to 0. Substitute x is equal to pi here. Pi minus pi 0, t tends to 0. So let us change the limit in terms of t. So limit t tending to 0 of sin t divided by pi times t. And we can apply the formula limit extending to 0 of sin x divided by x is 1. Let us use this formula. So limit t tending to 0 of sin t by t becomes 1. Therefore, we will get 1 by pi times 1, which is 1 by pi. Now question 16. Limit extending to 0 of cos x divided by pi minus x. If we substitute the limit value x as 0, the denominator doesn't become 0. Let us substitute the limit value directly. We get cos 0 divided by pi minus 0, which is pi. Cos 0 is 1. Therefore, the answer is 1 divided by pi. Question 17. Limit extending to 0 of cos 2x minus 1 divided by cos x minus 1. Let us take out a negative sign from both numerator and denominator and cancel these two negative signs. We get limit extending to 0 of 1 minus cos 2x is 2 sin square x divided by, and 1 minus cos x is 2 sin square x by 2. We can cancel these two 2's. Limit extending to 0 of, I can write sin x as 2 sin x by 2 cos x by 2 the whole square divided by sin square x by 2. Or we may divide both numerator and denominator by x square, and you can apply the limit for numerator and denominator separately. Limit extending to 0 of, let us distribute the square. We get 4 multiplied with sin square x by 2 multiplied with cos square x by 2 divided by sin square x by 2. Now we can apply the limit. Cos square 0 by 2. 0 by 2 is 0 and cos 0 is 1. 1 square is 1. Therefore, the answer is 4. Question 18. Limit extending to 0 of ax plus x cos x divided by b sin x. Let us divide each and every term by x. Limit extending to 0 of ax divided by x will become a, x cos x divided by x will be cos x, and in the denominator we will have sin x divided by x. Now let us apply the limit for each and every term. Limit of a constant is the same, plus cos 0, which is 1, divided by b times limit extending to 0 of sin x by x is 1. Let us write the formula. Therefore, the answer is a plus cos 0 is 1 divided by b. Till we apply the limit value, we have to keep writing limit extending to 0 in each and every step. Once you apply the limit, no need to write the limit. Question 19. Limit extending to 0 of x times secant x. Direct substitution we will do. 0 into secant 0. Secant 0 is 1. So 0 into 1 is 0. The answer is 0. 20th question. limit x tending to 0 of sin ax plus bx divided by ax plus sin bx, and a plus b are not equal to 0. This is the given condition. Limit x tending to 0 of, I am going to divide each and every term by x. So I get sin ax divided by x, bx divided by x will become b, divided by ax divided by x is a, and here I will get sin bx divided by x. But to use limit x tending to 0 of sin x by x formula, I need a here. So let us multiply and divide the first term by a, and multiply and divide this second term of the denominator by b. Keep writing the limit in every step till you apply the limits. Now I am going to apply the limits, so no need to write that limit extending to 0. A into, we are using the formula limit extending to 0 of sin x divided by x is 1. But the limit is extending to 0. So as x tends to 0, ax also tends to 0. Similarly, bx also tends to 0. Therefore, a into, by that formula it becomes 1. B is a constant. Here a is a constant, and b into 1. Therefore, the answer is a plus b divided by a plus b, which is 1. Question 21. Limit x tending to 0 of cosecant x minus cot x. If we directly apply the limit, cosecant 0 is not defined. Sin 0 is 0, cosecant 0 is not defined. Similarly, cot 0 is also not defined. So let us simplify this function first. Keep writing the limit in every step till you apply the limit value. Cosecant x is 1 divided by sin x, and cot x is cos x divided by sin x. Let us take LCM. Sin x, limit extending to 0 of sin x, and the numerator becomes 1 minus cos x, which is equal to limit extending to 0 of, keep writing the limit in every step till you apply the limit value. 1 minus cos x is 2 sin square x by 2, and denominator can be written as 2 sin x by 2 and cos x by 2. Let us cancel the common factors. Limit extending to 0 of sin divided by cos tan x by 2 it becomes. Apply the limits, so don't write limit extending to 0. It becomes tan of 0 by 2, which is 0, and tan 0 is 0. Question 22. Limit extending to pi by 2 tan 2x divided by x minus pi by 2. Let us use substitution. We will take the denominator as t. So x will be pi by 2 plus t. As x tends to pi by 2, t tends to 0. Substitute here. X as pi by 2 minus pi by 2, t becomes 0. Now let us change the limit question to t variable. Limit t tending to 0 of tan 2 times x is pi by 2 plus t divided by x minus pi by 2 is t. Once you change the variable, in this step you should not have x. Everywhere you should have t variable. This is equal to limit t tending to 0 of, let us distribute this 2. It becomes pi plus 2t and divided by t. Limit t tending to 0 of pi plus theta is the third quadrant angle. In the third quadrant, tan is positive. So it is tan 2t divided by t. Now we can multiply and divide by 2. Or you may change that tan in terms of sine and cos and then apply the limits. We know that limit extending to 0 of tan x divided by x is 1. And here, as x tends to 0 or t tends to 0, 2t also tends to 0. Therefore, this term becomes 1. 2 times 1, the answer is 2. Twenty-third question. Find limit extending to 0 of f of x and limit extending to 1 of f of x, where f of x is, we have two different definitions, 2x plus 3 for x less than or equal to 0 and 3 times x plus 1, x greater than 0. Both are polynomial functions. I told you we don't have any problem with polynomial functions because polynomials are defined for all real values. But the definition has been split at 0. We need to do LHL and RHL. LHL is limit extending to 0 minus of f of x. That means x approaches 0 from the left side of 0. That is the meaning of writing 0 minus. For 0 minus, we need to use less than 0 definition, which is 2x plus 3. I told you that polynomials are defined for all real values. We don't have not defined case. So we can directly substitute this limit value. Whether it is 0 minus or 0 plus, for polynomials, direct substitution is possible because the function is defined for all real values. So 2 times 0 is 0. 0 plus 3 is 3. Now let us find RHL. Limit extending to 0 plus of f of x. Limit extending to 0 plus f of x is, for 0 plus we have to use greater than 0 definition. So we must, therefore we have to use 3 times x plus 1 function. Again, this is a polynomial. Polynomials are defined for all values. This polynomial is defined at x is equal to 0. So we can directly substitute 0 value here because the function is defined at 0. Both the limit values are 3. LHL equal to RHL is equal to 3. Therefore, the limit exists. Therefore, limit extending to 0 of f of x. If I write extending to 0, 0 minus as well as 0 plus both are included, is equal to 3. This is the answer. For the same function f of x, we need to calculate limit extending to 1 of f of x. Now the definition has been split for less than or equal to 0 and greater than 0. Now we have to calculate the limit at 1. So on the left side of 1 or on the right side of 1, when we take very close value on the left side or right side of 1, both are going to be greater than 0. So we need not do LHL, RHL for the limit value 1. So we can combine and do limit extending to 1. 1 is greater than 0, so I need to use 3 times x plus 1. No need to do LHL, RHL for x is equal to 1. Even if you use LHL, RHL, you will use the same function 3 times x plus 1, which gives you the same answer. Here this is a polynomial. Again I am repeating, polynomials are defined for every real value. So we can directly substitute the limit value. 3 times 1 plus 1, 2. Therefore the answer is 6. Question 24. Find limit extending to 1 of f of x, where f of x is equal to x square minus 1 when x is less than or equal to 1, and minus x square minus 1 when x is greater than 1. We need to find limit extending to 1 of f of x. Now see the definition of the function. It has been split at 1. So for less than or equal to 1, the definition of f of x is different. For greater than 1, the definition of f of x is different. So we cannot combine the limits and do. Therefore, we need to do LHL, RHL. LHL is limit extending to 1 minus f of x. That is, x approaches 1 from the left side of 1. Very close value of 1, but on the left hand side we will take. Limit extending to 1 minus. For 1 minus, we use less than 1 definition, which is x square minus 1. This is again a polynomial. This function is defined at 1. So no problem in substituting the limit value 1 directly. 1 minus 1, the answer is 0. The problem arises only when the function is not defined or when you get 0 by 0 form. Now limit extending to 1 plus f of x. So x approaches 1 from the right side of 1. Limit extending to 1 plus. We have to use x greater than 1 definition. This definition has to be used. So minus x square minus 1. Polynomials are defined at all real values. So let us substitute 1. Minus 1 square is 1, minus 1, the answer is minus 2. So LHL is not equal to RHL. Therefore, limit extending to 1 of f of x does not exist. So LHL and RHL are not equal means there is a gap in the graph of this function f of x at x is equal to 1.